Hello everyone. Today we are going to analyze this beam using Kani's method. In this beam, the support C settles by 0.002 meter. The flexural rigidity EI is given as 8000 kilonewton meter square. Before starting the analysis, let us see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, we have 2-point loads, 9 kilonewton and 18 kilonewton. 9 kilonewton is acting at a distance of 2 meter from the point A. 18 kilonewton is acting at a distance of 4 meter from the point A. In the span BC, we have uniformly varying load. It is maximum in the center, 24 kilonewton per meter. In the span CD, we have uniformly distributed load, 18 kilonewton per meter. It is acting for the full span. Length of AB is 6 meter. Length of BC is 4 meter. Length of CD is also 4 meter. In this beam, all of the spans are having different moment of inertias. For the span AB, the moment of inertia is 1.5i. For the span BC, it is 3i. And for the span CD, it is 2i. Now let us find the fixed end moments. First, let us find them in the span AB. In the span AB, we have two eccentric point loads, 9 kilonewton and 18 kilonewton. The formulas to find the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. Let us apply the values in the formulas. For this point load, A is 2, B is 4, and for this point load, A is 4 and B is 2. After the calculation, for MFAB, we are getting minus 16, and for MFBA, we are getting 20. Now, let us find the fixed end moments in the span BC. In the span BC, we have symmetrical, uniformly varying load. The formulas to find the fixed end moments are minus 5WL square upon 96 and positive 5WL square upon 96. Here W is 24 and L is 4. Let us apply them. The support C sinks by 0.002 meter. So we have to find the fixed end moments due to the sinking. The formula to find the fixed end moments due to sinking is 6EI delta upon L square. If the sinking occurs on the left side of the span, the fixed end moments due to sinking will be positive. If it occurs on the right side of the span, the fixed end moments due to sinking will be negative. Since the sinking occurs on the right side, the fixed end moments due to sinking will be negative. In this formula, let us apply the values. EI is given in the question as 8000 kilonewton meter square. Let us apply that. For the span BC, the moment of inertia is 3i. So we have to multiply the EI value with 3. Delta is 0.002. L is 4. When we calculate this, we will get minus 18. In the points B and C, the fixed end moments due to sinking will be same. So for MFCB, we can apply this value directly. No need to find one more time. After the calculation, for MFBC, we are getting minus 38, and for MFCB, we are getting 2. Now let us find the fixed end moments in the span CD. In the span CD, we have uniformly distributed load 18 kilonewton per meter. The formulas to find the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Here W is 18, L is 4. Let us apply them. We know that the support C sinks by 0.002 meter. So we have to add the fixed end moments due to sinking. We know the formula for the fixed end moments 6EI delta upon L square. In this span, the sinking occurs on the left side. So the fixed end moments due to sinking will be positive. The moment of inertia for the span CD is 2I. So we have to multiply EI with 2. Delta is 0.002 and L is 4. After the calculation, for MFCD we are getting minus 12 and for MFDC we are getting 36. In the Kani's method, we have to find the rotation factor. For that, we have to find the stiffness. Let us see the formulas to find the stiffness in the joints. If the fare end is fixed, the formula is 4EI upon L. If the fare end is hinged or with roller support, the formula is 3EI upon L. If the fare end is continuous, the formula is 4EI upon L. In the joint B, first let us find the stiffness for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the fare end is fixed, the formula is 4EI upon L. For BA, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I. Length of BA is 6. Let us apply that. After calculation, for the stiffness of BA, we are getting EI. Now let us find the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous. If the fare end is continuous, the formula for the stiffness is 4EI upon L. The moment of inertia for BC is 3I. So instead of I, we have to apply 3I. Length of BC is 4. Let us apply that. After calculation, for the stiffness of BC, we are getting 3EI. Now in the joint C, let us find the stiffness for CB. For that, from the joint C, we have to look at the point B. The point B is continuous. We know that if the fare end is continuous, the formula for the stiffness is 4EI upon L. Moment of inertia for CB is 3I and length is 4. Let us apply that. After calculation for the stiffness of CB, we are getting 3EI. Now let us find the stiffness for CD. For that, from the point C, we have to look at the point D. In the point D, there is a fixed support. If the fare end is fixed, the formula for the stiffness is 4EI upon L. The moment of inertia for CD is 2I and length is 4. Finally, for the stiffness of CD, we are getting 2EI. Now let us find sigma k. In the joint B, we have calculated two stiffness values. We have to add both of them. After adding, we are getting 4EI. In the joint C, we have calculated two stiffness values. We have to add both of them. After adding, we are getting 5EI. Now let us find the rotation factors. The formula is minus 1 upon 2 into k upon sigma k. We have already calculated k and sigma k values. Using the formula, we can find the rotation factors. In the Kani's method, we have to make boxes like these in the joints. Now let us enter the fixed end moments. M of AB here, M of BA here, M of BC here, M of CB here, M of CD here, and finally M of DC here. In the joints, we have to add the fixed end moments. When we add these two values, we will get minus 18, and when we add these two values, we will get minus 10. Now let us enter the rotation factors. The rotation factor for BA here, for BC here, for CB here, and for CD here. In the Kani's method, in the joints, we have to find the rotation contributions. In the joint B, we have to find the contributions M dash BA and M dash BC. And in the joint C, we have to find M dash CB and M dash CD. The formula to find the rotation contribution is summation of rotation contributions at far end plus summation of fixed end moments into rotation factor. Now let us find M dash BA. M dash BA is located in the joint B. For the joint B, the fair ends are the point A and the point C. In the point A, we have a fixed support. In the fixed support, the rotation contribution will be always 0. In the point C, initially m dash CB will be 0. So for the summation of rotation contributions at far end, we have 0 plus 0. The summation of fixed end moments is minus 18. The rotation factor for BA is minus 0.125. Finally, for M dash BA, we are getting 2.25. Now let us find M dash BC. For M dash BA and M dash BC in the formula, all of the values will be same except the rotation factor. The rotation factor for BC is minus 0.375. After the calculation for M dash BC, we are getting 6.75. Let us enter M dash BA and M dash BC. Now let us find M dash CB. M dash CB is located in the joint C. For the joint C, the fair ends are the point B and the point D. In the point B, the rotation contribution is 6.75. In the point D, we have a fixed support. We know that in the fixed support, the rotation contribution will be 0. So the summation of rotation contributions at fair end is 6.75 plus 0. The summation of fixed end moment is minus 10. The rotation factor for CB is minus 0.3. After the calculation for M dash CB, we will get 0.975. We know that for M dash CB and M dash CD, in the formula, all of the values will be same except the rotation factor. The rotation factor for CD is minus 0.2. After the calculation for M dash CD, we are getting 0.65. Let us enter M dash CB and M dash CD. Now we have finished the first cycle. We are going to start the second cycle. Now let us find M dash BA and M dash BC. We know that in the point A, we have a fixed support. So the rotation contribution will be 0. In the point C, now we have the rotation contribution 0.975. So for the summation of rotation contributions at far end, we have 0 plus 0.975. The summation of fixed end moments is minus 18. The rotation factor for BA is minus 0.125 and for BC is minus 0.375. After the calculation for M-BA we are getting 2.128 and for M-BC we are getting 6.384. Let us apply them. Now let us find M-CB and M-CD. In the point B, we have the latest rotation contribution 6.384. We know that in the point D, we have a fixed support. So the rotation contribution will be 0. So for the summation of rotation contributions at far end, we have 6.384 plus 0. The summation of fixed end moments is minus 10. Let us enter the rotation factors. For CB, it is minus 0.3, and for CD, it is minus 0.2. After the calculation, for M-CB, we are getting 1.085, and for M-CD, we are getting 0.723. Let us enter them. We have finished the second cycle. Let us start the third cycle. Let us find M-BA and M-BC. In the point A, the rotation contribution will be 0. In the point C, we have the latest rotation contribution 1.085. So for the summation of rotation contributions at afferent, we have 0 plus 1.085. The summation of fixed end moments is minus 18. Let us apply the rotation factors. For BA, it is minus 0.125, and for BC, it is minus 0.375. After the calculation, for M-BA, we are getting 2.114, and for M-BC, we are getting 6.343. Let us apply them. Now let us find M-CB and M-CD. In the point B, now we have the latest rotation contribution 6.343, and in the point D, the rotation contribution is 0. So for the summation of rotation contributions at afferent, we have 6.343 plus 0. The summation of fixed end moments is minus 10. Let us apply the rotation factors. For CB, it is minus 0.3, and for CD, it is minus 0.2. After the calculation, for M-CB, we are getting 1.097, and for M-CD, we are getting 0.731. Let us apply both of them. We have finished the third cycle. Let us start the fourth cycle. Let us find M-BA and M-BC. In the point A, the rotation contribution is 0. In the point C, we have the latest rotation contribution 1.097. So for the summation of rotation contributions at afferent, we have 0 plus 1.097. The summation of fixed end moments is minus 18. Let us apply the rotation factors. For BA, it is minus 0.125, and for BC, it is minus 0.375. After the calculation, for M-BA, we are getting 2.113, and for M-BC, we are getting 6.338. Let us apply both of them. Now let us find M-CB and M-CD. In the point B, we have the latest rotation contribution 6.338. In the point D, the rotation contribution is 0. So for the summation of rotation contributions at afferent, we have 6.338 plus 0. The summation of fixed end moments is minus 10. Then let us apply the rotation factors. For BA, it is minus 0.3, and for CD, it is minus 0.2. After the calculation, for M-CB, we are getting 1.099, and for M-CD, we are getting 0.732. Let us apply them. We have finished the fourth cycle. We don't have to go for the fifth cycle, because in the third and fourth cycle, we are getting approximately equal values. Now we are going to find the final moments. We know the formula to find the final moments. Fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at far end. Let us make a table. In the table, first let us enter all of the members. Then let us enter the fixed end moments. Then let us enter 2 into near end rotation contributions. We know that in the points A and D, there are fixed supports. In the fixed supports, the rotation contributions will be 0. So for AB and DC, 2 into 0. For BA, the near end rotation contribution is 2.113. So 2 into 2.113. For BC, it is 6.338. So 2 into 6.338. For CB, it is 1.099. So 2 into 1.099. For CD, it is 0.732. So 2 into 0.732. Using the arrows, we can enter far end rotation contributions. Now let us add these three values. After adding, we will get the final moments. Now we are going to find the vertical reactions. First, let us take the span AB and find the vertical reactions. In the span AB, we have the moments MAB and MBA. MAB is acting in the anti-clockwise direction and MBA is acting in the clockwise direction. In this span, first let us find the reaction RA. For that, let us take moment about B. In this case, we are moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction, so that will be positive and the distance is 6. So 6 RA. The point load 9 kN is acting in the anti-clockwise direction, so it will be negative and the distance is 4. The point load 18 kN is acting in the anti-clockwise direction, so that will be negative and the distance is 2. This movement is acting in the anti-clockwise direction, so that will be negative, and this movement is acting in the clockwise direction, so that will be positive. Finally, for RA, we are getting 10.28 kilonewton. Now let us apply the rule sigma V is equal to 0. RA and RB1 are acting upwards, so both of them are positive. These two loads are acting downwards, so both of them are negative. For RA, we can apply 10.28. Finally, for RB1, we are getting 16.72 kilonewton. Now, let us take the span BC and find the vertical reactions. In the span BC, we have two movements, MBC, which is acting in the anti-clockwise direction, and MCB, which is acting in the clockwise direction. In this span, first let us find RB2. For that, let us take a moment about C. RB2 is acting in the clockwise direction, so that will be positive and the distance is 4. So for RB2, the uniformly varying load is acting in the anti-clockwise direction, so it will be negative. For this kind of load, we have to multiply the area with the centroidal distance. It is a triangle. We know the formula for the area of a triangle, half into breadth into height. Here the breadth is 4 and the height is 24. Now let us find the centroidal distance. This is a symmetrical triangle, so the centroid lies in the center. To find the centroid, we have to divide the length 4 by 2. This movement is acting in the anti-clockwise direction, so that will be negative, and this movement is acting in the clockwise direction, so that will be positive. Finally, for RB2, we are getting 27.42. Now let us apply this rule and find RC1. RB2 and RC1 are acting upwards, so both of them are positive. The UVL is acting downwards, so that will be negative. To convert the UVL load into point load, we have to find its area. We already know its area. Let us apply that. Finally, for RC1, we are getting 20.58 kilonewton. Now let us take the span CD and find the reactions. In the span CD, we have the movement MCD, which is acting in the anti-clockwise direction, and MDC, which is acting in the clockwise direction. By taking moment about D, we can find RC2, and by applying this rule, we can find RD. In the point B, we have calculated the reactions 2 times, RB1 and RB2. Let us add both of them so that we will get RB. In the similar way, let us add RC1 and RC2 so that we will get RC. Now, using the reactions and loads, we can draw the shear force diagram. Here I have made the calculations for the shear force diagram. Here you can see the shear force diagram. Now let us draw the free movement diagram. To draw the free movement diagram, we have to consider every span as a separate simply supported beam. First, let us take the span AB and see how to draw this diagram. Here I have converted the span AB into a simply supported beam. Let us take moment about B and find RA. By applying this rule, we can find RB. RA is 12 and RB is 15. When we multiply 12 into 2, we will get 24. And when we multiply 15 into 2, we will get 30. Now let us take the span BC. Here we have uniformly varying load. Here we have to apply the formula WL square upon 12. Using the formula we are getting the ordinate 32. Using that we can draw this diagram. In the span CD we have uniformly distributed load. Here we have to use the formula WL square upon 8. Using the direction of the end movements, we can draw the end movement diagram. By combining free movement diagram and end movement diagram, we can draw the bending moment diagram. Now we are going to end this session. Thank you for watching this video.